November 7, 1943, Rechlin Airfield, Germany. Hauptmann Hans-Werner Lerche circles a captured American fighter, and what he sees makes no sense. The aircraft is massive, nearly twice the weight of a Messerschmitt. The cowling alone looks bigger than some fighters' entire fuselages. To German eyes, trained on lean, efficient, mathematically perfect designs, the Republic P-47 Thunderbolt looks like a joke. "This is wasteful engineering," one engineer will write in his report. "We could reduce weight by 1,000 kilograms and still have adequate strength." But another engineer sees something else, something terrifying. 3 days earlier, a 22-year-old American pilot made a navigation error and landed this aircraft completely intact at a German airfield. He thought it was British. It wasn't. Now the Luftwaffe has their first chance to understand the fighter that's been tearing through German formations for months. The fighter that comes back with battle damage that should be fatal. The fighter that keeps multiplying no matter how many they shoot down. What German engineers are about to discover will reveal a truth that will haunt them for the rest of the war. America isn't trying to build the best fighter. They're building a fighter they can make by the thousands, and there's no tactical solution to that problem. This is the story of how crude engineering defeated technical perfection, how a flying milk jug broke the back of the Luftwaffe, and how one captured aircraft revealed the real reason Germany was losing the war. This is the story of the P-47 Thunderbolt, and it begins with a young pilot who flew straight into enemy territory. November 4, 1943. Steeple Morden, England. Second Lieutenant William Edward Roach is 22 years old, from Pennsylvania, and he's about to fly his third combat mission. Today's mission is straightforward: escort B-26 Marauder medium bombers attacking German airfields in occupied France. Roach is flying as a spare. If any primary aircraft develops problems, he replaces them. If everything runs smoothly, he turns back early. 10 minutes after takeoff, Lieutenant John Lanier's engine starts acting up. Oil pressure fluctuates, temperature climbs. Lanier can't continue. Roach moves up from spare position into Yellow Flight's number 4 slot. He's committed now. The weather over northern France that morning is brutal. Thick clouds extend from near ground level up to 20,000 feet. Visibility inside the clouds, 0. Outside temperature, minus 15 degrees Celsius. Ice forms on wings and canopies. Navigation is entirely by instruments and dead reckoning. No visual reference points, just gray clouds in every direction. The B-26 bombers try to locate their targets, but conditions are impossible. The mission commander aborts. The bombers jettison their loads over water and turn for home. The P-47s turn with them. That's when everything goes wrong. The return flight encounters severe headwinds that weren't in the weather forecast. Wind speeds exceed 100 miles per hour at altitude, blowing directly from England toward France. The P-47s are fighting massive headwinds while trying to reach home. Fuel consumption rates skyrocket. Yellow Flight descends through the clouds. Roach loses visual contact with his formation in the thick overcast. He flies by instruments, maintaining what he believes is the correct heading for England. When he breaks out of the clouds at 8,000 feet, he expects to see the English Channel. Instead, he sees French farmland. The headwinds have blown him far off course. His fuel gauge shows maybe 40 minutes of flying time remaining, not enough to find England. Then he spots an airfield below, grass runways, buildings. It looks like a British advanced landing ground. Roach decides to land, refuel, and continue home. He circles once, lowers landing gear and flaps, and makes a smooth landing. A jeep meets him and leads him to a parking area. Roach shuts down the engine and opens the canopy. That's when he sees Wehrmacht soldiers carrying rifles approaching his aircraft. He's landed at Carpiquet Airfield near Caen, France, a Luftwaffe base. He's flown straight into enemy territory. The German soldiers pull Roach from the cockpit. Within hours, he's on a truck to a POW camp. Within a day, he's at Stalag Luftwaffe near Barth, Germany, where he'll remain until Soviet forces liberate the camp in May 1945. 3 other pilots from the 358th Fighter Squadron are lost that same day, all from fuel exhaustion caused by the unexpected headwinds. But Roach's capture is different. For the Luftwaffe, this is extraordinary luck. They've been fighting P-47s for months, but have never captured one intact and flyable. Crashed aircraft are usually too damaged for useful evaluation. Burned wreckage reveals little about how the aircraft is actually built. This is different. The aircraft is perfect. Engine undamaged, structure intact, systems complete. Even the fuel tanks are still in place, though empty. The captured Thunderbolt, serial number 4222490, nicknamed Beetle, squadron code YFU, stays at Carpe for 2 days. Luftwaffe ground crews photograph every detail. They paint over the American stars with German crosses. They paint the nose cowling yellow, the standard Luftwaffe marking for captured aircraft, warning anti-aircraft gunners not to shoot. Then, the Thunderbolt is flown to Rechlin, Germany's primary aircraft test and evaluation center. And German engineers are about to learn something that will change their understanding of how America fights wars. Hauptmann Hans-Werner Lerche is Rechlin's senior test pilot. He's flown over 100 different aircraft types by 1943, including multiple captured Allied fighters. He's methodical, experienced, highly skilled. On his first walk-around of the Thunderbolt, he notices the size. German fighters are compact. The Bf-109's cockpit is so tight that tall pilots can't fly it. The Thunderbolt's cockpit is enormous. Pilot could stretch, adjust position, even stand halfway up if needed. Lerche starts the Pratt & Whitney R2800 engine, 18 cylinders in 2 rows, air-cooled, displacing 46 liters. The radial engine fires with a deep rumble that shakes the entire aircraft. German fighters use inline liquid-cooled engines that run smooth and refined. This radial sounds crude, almost agricultural, but it runs perfectly. Temperature stable, oil pressure correct, no vibration. Lerche taxis to the runway. The Thunderbolt feels heavy, sluggish. He advances the throttle and begins his takeoff run. The aircraft needs nearly 500 meters of runway. German fighters need half that distance. Once airborne, Lerche climbs to test altitude. Below 15,000 feet, the Thunderbolt feels exactly as German pilots have reported. Heavy, poor turn rate, mediocre acceleration. Every maneuver requires planning. But above 20,000 feet, something changes. The turbocharger engages fully. Power increases dramatically. The engine that seemed crude at low altitude suddenly becomes efficient and strong. Lerche pushes the throttle forward and feels genuine acceleration. He rolls into a dive. The Thunderbolt dives faster than any fighter he's flown. The heavy airframe that seemed like a liability becomes an advantage, building speed quickly and holding it through the dive. He pulls out and climbs vertically. The Thunderbolt maintains energy through the climb. Above 25,000 feet, roll rate is excellent. Controls that felt mushy low down become crisp and responsive. When Lerche lands after 40 minutes of testing, his assessment is clear. The Thunderbolt is built differently. Everything about it contradicts German engineering principles, but it works. Over the next several days, German engineers conduct the most thorough evaluation of an American fighter they've ever performed. Every system is examined, every component is measured, every design decision is analyzed, and what they discover changes everything. The first revelation comes from examining the structure. German aircraft are masterpieces of weight optimization. Every component is engineered to minimum weight while maintaining adequate strength. Engineers calculate stress loads with extreme precision. They use the thinnest aluminum that can handle expected forces. They eliminate every unnecessary gram. The result: light, efficient, fast, agile aircraft. The Thunderbolt represents the opposite philosophy. The fuselage uses aluminum sheet metal nearly 2 millimeters thick, where German practice uses 1 millimeter or less. The longerons, main structural members running the length of the fuselage, are built from channel sections 5 millimeters thick. German longerons typically measure 3 millimeters. The formers are spaced 30 centimeters apart. German practice spaces them 50 to 60 centimeters apart to save weight. German engineers calculate that the Thunderbolt's fuselage is overbuilt by a factor of nearly 2.1. The structure can withstand load. Factors of 15G before failure. Fighter requirements specify 8G capability. The fuselage weighs approximately 1,200 kilograms more than necessary by German engineering standards. One German structural engineer writes in his evaluation notes, "The Americans build bridges when they should build aircraft. This structure is absurdly overbuilt. We could reduce weight by 1,000 kilograms, and still have adequate strength for any combat maneuver. This is wasteful engineering. But another engineer recognizes the real purpose. He writes, "The overbuilt structure is not about flight performance. It is about manufacturing and field operations. With this much excess strength, manufacturing tolerances can be much wider. Less skilled workers can build components. If rivets are not perfect, the structure compensates. If welds are slightly defective, the excessive strength means they still hold. Battle damage that would catastrophically fail our lightweight structures is survivable here." The Americans are not designing for maximum performance. They are designing for mass production by unskilled labor and battlefield survival. That insight explains everything German pilots have been reporting from combat. Thunderbolts returning to base with battle damage that should be fatal. Wings with dozens of holes still generating lift. Fuselages riddled with cannon fire, still maintaining structural integrity. The overbuilt design means damage has to be extraordinarily severe before causing catastrophic failure. The numbers tell the story. Thunderbolt empty weight, 4,190 kilograms. Messerschmitt Bf 109G empty weight, 2,700 kilograms. Focke-Wulf 190A empty weight, 3,200 kilograms. The Thunderbolt is 65% heavier than a 109 and 40% heavier than a 190. That weight penalty directly impacts climb rate, turn rate, and acceleration, but it provides massive structural margins that keep pilots alive. The second discovery comes from the engine. The Pratt & Whitney R2800 radial engine weighs over 1,000 kilograms by itself. German engineers prefer inline liquid-cooled engines because they are more aerodynamic and efficient. Radials are considered old technology. German engineers run the captured engine on a test stand at full power. They deliberately damage it to test durability. They remove spark plugs from 3 cylinders. The engine keeps running with reduced power. They puncture the oil cooler. Oil pressure drops, but the engine continues operating. They shoot bullets through 6 cylinders. The engine runs rough but doesn't seize. A German inline engine with its liquid cooling system would fail immediately from coolant loss. Radiator damage means engine failure within minutes. The Thunderbolt's radial engine can lose multiple cylinders, suffer oil system damage, take battle damage that would destroy any German fighter, and still bring the pilot home. It isn't about performance, it's about survival. The third discovery is the armament philosophy. 850 caliber Browning M2 machine guns, 4 in each wing. Total ammunition capacity, 3,400 rounds, 425 rounds per gun. That's nearly 20 seconds of continuous fire. German fighters typically carry enough ammunition for 5 seconds of firing time. American doctrine isn't about precision, it's about volume. German pilots train for years learning deflection shooting and gunsight discipline. American pilots receive months of training and learn combat tactics in the field. So Americans compensate with ammunition. Miss the first burst? Fire again. Keep shooting until something hits. 8 machine guns are far easier to manufacture than cannons. The ammunition is simpler, cheaper, produced in enormous quantities. The entire system is designed for mass production and minimal training requirements, not engineering excellence. Every system in the Thunderbolt prioritizes industrial efficiency over technical perfection. It's heavier, simpler, tougher, easier to build, easier to maintain, easier to fly, easier to repair. It isn't the best possible fighter, it's the fighter that can be produced by the millions and flown by pilots with minimal training. After testing at Rechlin is complete, the captured Thunderbolt is transferred to a special Luftwaffe unit, Circus Rosarius. Officially designated the 2nd Staffelversuchsverband Oberbefehlshaber der Luftwaffe, it's commanded by Hauptmann Theodor Rosarius. Circus Rosarius has one mission: demonstrate captured Allied aircraft to frontline Luftwaffe units. The unit tours German airbases across occupied Europe, showing German pilots what enemy aircraft look like up close. Explaining their characteristics, strengths, weaknesses, German pilots can examine the aircraft, sit in cockpits, watch demonstration flights. Through early 1944, Rosarius flies the Thunderbolt to bases in Germany, Austria, and France. German pilots crowd around the big American fighter, surprised by its size and weight. Rosarius explains what Rechlin learned. The Thunderbolt is slow to turn below 15,000 feet, attack from below in a climbing turn to get inside its radius. But above 20,000 feet, don't turn with it. Use speed, diving attacks, hit-and-run tactics. Never assume battle damage will bring it down. Keep shooting until you see structural failure. Many German pilots look skeptical. The Thunderbolt seems so heavy, so awkward. How much of a threat could it really be? They're experienced. They've been fighting for years. They know air combat. What could this American machine teach them? Then German pilots start dying at increasing rates. January 1944. American Thunderbolt production reaches industrial scales Germany cannot match. Republic Aviation's original plant in Farmingdale, Long Island, covers over 1 million square feet of factory space, employing 23,000 workers in 3 shifts. The facility produces approximately 200 P-47s per month, 1 complete aircraft every 3.6 hours around the clock. The Evansville, Indiana plant adds another 100 aircraft per month from 1.2 million square feet of factory space with 18,000 workers. Curtiss-Wright Corporation in Buffalo manufactures P-47Gs under license, adding approximately 50 aircraft monthly. Combined output, over 350 Thunderbolts per month, over 11 aircraft per day arriving at ports for England. But the production advantage extends beyond aircraft. The United States Army Air Force's training pipeline produces over 2,000 newly qualified fighter pilots monthly from bases across America. New pilots receive approximately 300 hours of flight training, including 50 hours in their combat aircraft type. They arrive in England, join squadrons with experienced leaders who mentor them through first missions. If they survive initial combat, skills improve rapidly through careful instruction. German pilot training has collapsed. Fuel shortages limit flying time. Aircraft shortages mean training on obsolete types. Instructor shortages mean inexperienced teachers. New German pilots arrive at combat units with less than 100 hours total time, sometimes as few as 10 hours in their assigned aircraft. They face American pilots with 3 times the training and often months of combat experience. German pilot losses exceed replacement rates. Veterans die. New pilots die on first missions. Squadron strength decreases despite new aircraft from factories. By January 1944, American Thunderbolt pilots have 9 months of combat experience. They have learned what works. They stop trying to turn with German fighters at low altitude. Instead, they climb to 30,000 feet before entering German airspace. When they spot enemy aircraft below, they dive from above, building speed to over 400 miles per hour. They fire bursts from 8 guns, then zoom back to altitude before German fighters can respond. The 8 machine guns prove brutally effective. American pilots don't need perfect aim. They point generally at the target and hold the trigger. With 400 rounds per gun, they can afford to miss. The sheer volume of bullets creates a killing zone 30 meters wide and 100 meters long. The 50 caliber Browning fires rounds weighing 43 grams at 890 meters per second. 8 guns firing together produce 34 kilograms of bullets per second. A 3-second burst puts over 100 kilograms of metal into the target area. German pilots report that Thunderbolt attacks feel like flying into walls of metal. Rounds don't need to hit critical components. Multiple hits anywhere cause cumulative structural damage. Wingskins crack, control surface hinges fail, engine cowlings shred, fuel tanks leak, cockpit impacts stun pilots even when armor stops penetration. The psychological impact is severe. German pilots who dominated air combat for years suddenly feel vulnerable. The Thunderbolts attack from above with overwhelming firepower. German pilots can't climb fast enough to meet them, can't turn tight enough to evade, can't damage them enough to bring them down. And there are always more of them. Shoot down 1 Thunderbolt and 2 more appear. Combat loss statistics tell the story. In January 1944, 8th Air Force P-47 groups fly over 10,000 sorties. They claim 114 enemy aircraft destroyed in air combat. They lose 38 Thunderbolts to all causes, including flak, mechanical failure, and combat. Kill ratio, 3.1 in favor of Americans. But more importantly, loss rates per sortie are microscopic. Less than 0.4% of sorties result in aircraft lost. German fighter units are losing 2 to 3% of aircraft per mission. The 56th Fighter Group, based at Boxted, England, illustrates American effectiveness perfectly. By January 1944, they have 9 months of experience. They know their aircraft's capabilities intimately. They've developed tactics that work. In January alone, the 56th destroys 78 German aircraft confirmed, plus dozens more unconfirmed. They lose 6 Thunderbolts total. The ratio, 13-1. Other Thunderbolt groups show similar improvements. 78th Fighter Group, 62 German aircraft destroyed, 4 Thunderbolts lost. 356th Fighter Group, 48 destroyed, 5 lost. Across all P-47 units, the pattern is consistent. Kill ratios heavily favor Americans. Loss rates remain low. Replacement aircraft and pilots arrive faster than losses occur. American strength grows while German strength declines. Major Gerhard Roth was one of the Luftwaffe's most successful night fighter pilots. 58 confirmed aerial victories, all against RAF bombers at night. In February 1944, Roth attends a Zirkus Rosarius demonstration where Rosarius shows the captured Thunderbolt. Roth examines the American fighter and is struck by how different it is from anything the Luftwaffe flies. The overbuilt structure, the massive engine, the simple, rugged systems, everything designed for production and survival rather than performance and efficiency. Roth understands immediately what this represents. He says to his fellow officers after the demonstration, "We can shoot down 10 of these and 20 more arrive the next day. That's the real problem, not the aircraft, the production system behind them." German pilot losses accelerate through winter and spring 1944. February, Luftwaffe fighter strength on the Western Front drops 12%. March, losses reach 15%. April, losses hit 17%. The problem isn't aircraft production. Germany is building over 900 fighters monthly. The problem is pilots. Experienced pilots die faster than training schools can replace them. A newly trained German pilot with 200 hours of training and no combat experience survives an average of 3 missions before being killed. The Luftwaffe shortens training to increase pilot throughput. That makes it worse. Pilots with 100 hours of training die on their first mission. Americans have the opposite problem. They have too many trained pilots. Most have 300 hours of training, including 50 hours in their combat aircraft. They arrive in England, join operational units, fly first missions with experienced leaders. American replacement pilots have time to learn. If they survive their first 5 missions, survival probability increases dramatically. The Thunderbolt's ruggedness means mistakes don't always equal death. A pilot can be hit, damaged, and still make it home to learn from experience. German pilots in lighter, more fragile aircraft die from the same mistakes. By March 1944, average Luftwaffe pilot experience under 100 total flying hours. Average American Thunderbolt pilot experience over 300 hours. The experience gap means German pilots lose fights they should win based on aircraft performance alone, and the Thunderbolts keep coming in numbers. Germany can't match. Every day, more arrive at English ports. Every week, new pilots join squadrons. Every month, American strength increases while German strength decreases. When Germans shoot down a Thunderbolt, 2 more replace it within days. When Germans kill an American pilot, 2 trained replacements arrive within a week. The American system operates like a machine, producing aircraft and pilots faster than Germans can destroy them. Hans-Werner Lersch survived the war. He was captured by Allied forces in May 1945. In 1946, Lersch was recruited as part of Operation Paperclip, the American program bringing German scientists and engineers to the United States. He was sent to Wright-Patterson Air Force Base in Ohio, where he worked until 1968 evaluating aircraft and training test pilots. In the 1970s, he wrote a memoir titled Luftwaffe Test Pilot, Flying Captured Allied Aircraft of World War II. In his memoir, Lersch devoted an entire chapter to the P-47. He wrote that flying the Thunderbolt was his introduction to American engineering philosophy. Americans didn't build aircraft to be perfect. They built them to be good enough, then built thousands of them. I initially thought it was crude engineering. Years later, I understood it was brilliant strategy. Theodore Rosarius, commander of Zirkus Rosarius, was captured by Soviet forces in April 1945. He spent 5 years in Soviet prison camps before release in 1950. Before his death in 1979, Rosarius gave an interview to a West German television program. He was asked what lesson he learned from demonstrating captured aircraft. Rosarius said, "We showed German pilots Allied aircraft to help them understand enemy capabilities. But after the war, I realized we taught the wrong lesson. We showed pilots how to fight American fighters one-on-one. We should have shown them the factories, because the real threat wasn't the aircraft. It was the production system that built them. You could shoot down 100 Thunderbolts and it didn't matter because 150 more arrived that week. That's what Germany was fighting. Not pilots, not aircraft, the whole American industrial machine. And there was no tactical solution to that problem." The P-47 Thunderbolt became the most produced American fighter of World War II. Republic Aviation built 15,583 Thunderbolts between 1941 and 1945. That total exceeded combined production of all other American fighter types except the P-51 Mustang. To put that in perspective, Germany's total fighter production for all types combined from all manufacturers peaked at approximately 500 aircraft per month in summer 1944. America was building more P-47s alone than Germany built fighters total, and America was simultaneously producing thousands of P-51 Mustangs, P-38 Lightnings, F-6F Hellcats for the Navy, and numerous other aircraft types. The industrial capacity gap was insurmountable. Thunderbolts flew over 546,000 combat sorties during the war. In air-to-air combat, they destroyed more than 11,000 enemy aircraft. Ground strafing attacks accounted for another 9,000 enemy aircraft destroyed. Overall kill-to-loss ratio, 4.6 to 1, nearly 5 enemy aircraft destroyed for every Thunderbolt lost. Loss rates averaged 0.7% per mission, less than 1 aircraft loss per 1,000 sorties flown. Robert Johnson, who scored 27 aerial victories flying Thunderbolts with the 56th Fighter Group, survived an engagement where German fighters hit his aircraft over 200 times with cannon and machine gun fire. His engine was damaged, his controls were shot, his fuselage was riddled with holes, but the Thunderbolt kept flying and brought him home. Johnson said after the war, "No other fighter would have survived that level of damage. The Thunderbolt's toughness saved my life." Francis Gabreski, who scored 28 aerial victories in Thunderbolts to become the top-scoring American ace in Europe, emphasized the aircraft's maintainability. Crew chiefs could perform major repairs at forward airfields with basic tools and minimal parts. Aircraft damaged in morning missions could be repaired and flying again by evening. German fighters required specialized tools, trained technicians, and parts from central depots. Repair times were much longer. The Thunderbolt's maintenance advantage multiplied American numerical superiority because damaged aircraft returned to service faster. The Thunderbolt's success wasn't about being the best fighter. The P-51 Mustang was faster with longer range. The P-38 Lightning was more versatile. The Spitfire was more agile. But the Thunderbolt could be built faster, flown by less experienced pilots, maintained by mechanics with basic training, repaired with simple tools. It matched America's strengths, industrial capacity, resources, and the ability to train large numbers of adequate pilots quickly. German aircraft designers continued building technically superior fighters until war's end. The Messerschmitt Me-262 jet was the fastest operational aircraft of the war. The Focke-Wulf Ta-152 was probably the finest piston-engine fighter ever designed. All were engineering masterpieces. All were produced in numbers too small to matter. Germany built approximately 16,000 fighters in 1944, their peak production year. The United States built 96,000 that same year. The numbers weren't close. The captured Thunderbolt that German engineers examined in late 1943 was one aircraft. But it represented a fleet of 15,000. Behind that fleet stood factories, workers, resources, transportation networks, training schools, and the industrial capacity of a nation built for mass production. Germany's engineers understood individual machines brilliantly. America understood industrial systems. That difference decided the war. Wars are won through logistics, production capacity, and the ability to replace losses faster than enemies can inflict them. The Thunderbolt wasn't the best fighter of World War II, but it was the fighter that could be built in sufficient numbers to overwhelm technically superior opponents. Sometimes adequate but abundant beats, excellent but rare. And William Roach, the young pilot who accidentally gave Germany their first complete Thunderbolt, when asked about his capture years later, he'd say, "I made a navigation error that gave Germany their first complete Thunderbolt, but by the time they figured out what it meant, America had already built 10,000 more, so it didn't matter much." If this story reminded you that wars aren't won by the best weapons, they're won by the best systems, hit that like button. It helps us share more untold stories from World War II. Subscribe to World War II Ember to explore the hidden truths of history, the stories that reveal not just what happened, but why it mattered. And leave a comment. Tell us where you're watching from veterans to engineers, from history students to aviation enthusiasts. You're part of our community. Thank you for watching. And thank you for understanding that sometimes the crudest solution is the most brilliant one.